This podcast is brought to you by LMU Munich.
Okay, so where we left off this morning, I had just started talking about the basics of quantum field theory in curved spacetime, in particular just the simple minimally coupled scalar field. We had introduced action for it, Hamiltonian, talked about the Klein-Gordon equation and the Klein-Gordon inner product. And the next thing that one wants to do is to, and it's the same as you would do in flat space-time, is to sort of think about canonical quantization of this field. So I think I will assume that this is all fairly fresh since earlier today. And so what we will do now is look at quantization of scalar field. Continue that. And so the next thing is to write this field in terms of a complete set of orthonormal modes. And Kyriakos already told us about this morning, so I can do this fairly briefly. Imagine, so you simply write this up. So I here is sort of a shorthand for whatever indices you need to completely describe your field. And it's the usual thing. You have positive and negative frequencies. Like so. And of course you have to find these mode functions, so you look for solutions of the Klein-Gordon equation that satisfy the following properties. Now of course the way you would do it in Minkowski space is to use separation of variables, expand things in spherical harmonics. And when we look at a simple model later on with a spherical shell falling in, we can basically follow that line of attack. And so, like I said, they are orthonormal. The way we have our there's a minus sign here. Remember the norm was not positive definite. And then this is an important one. The positive and negative frequency modes will commute. Or that will follow from this. All right. And then we simply do canonical quantization. So we introduce commutation relations for these modes in the usual way. We identify a vacuum state. Which is such that all the positive frequency modes are going to annihilate it. And we will have some sort of Fock space basis, as usual. Where we have creation modes acting on this. And so we can have the AI1 to some, I guess you can have multiple particles in different modes, so bosons. And then you're going to have some normalization factor here.
Can you speak a bit louder?
Yes, I can try. So anyway, this is just standard here. So we have our basis for our, and then just to remind you how this works, if you're in Minkowski space, if this one is just really then we're going to, we know what these modes are, they're simply plane waves. We label them by momentum. In that case, some normalization factor here. Okay, and this guy here is just given by in the usual way. Okay, so this is how you would do in Minkowski space, and what you know there is that the operators so this is we're still talking about the Minkowski space-time example. So here, these guys are symmetry they generate symmetries. In fact, it's a subset of the Poincare transformations. And these symmetries, they leave the Minkowski vacuum invariant. And so as a result, if one does a change of basis, if one does a Poincare transformation, one is guaranteed that since the vacuum is invariant, if you take a state that has no particles in it, you do a Poincare transformation, you're still going to have a state that has no particles in it. Now this is no longer true when you're in curved space-time. In general, there are no symmetries. And so therefore you cannot assume anything like that. And this, of course, is where this Hawking effect is going to come from. Okay. And there's really no preferred set of coordinates. Well, of course, there are coordinates that might be more useful for a particular problem, but they're not fundamentally so there's no fundamental reason to pick one coordinate over another. And so therefore, this choice of positive frequency modes is not unique. All right. So we chose our modes. We wrote our field as a linear combination of them, but we can also choose some other set of modes. It's still the same field, but with another choice of modes, we would get a different expansion. So we're going to take a different set of modes. Let's call them, let's put a twiddle on top of them. Well, this is going to give us another expansion for the field. Where I put tildes on everything. And in particular, there will be a new vacuum now. Let me call it, put a tilde on the symbol for the vacuum. It's also now going to be annihilated by all my annihilation operators, but it's not the same vacuum as before. Now, it's a linear equation that we're dealing with, so of course I can write this thing in terms of either, so these are supposed to be a complete set of orthonormal modes, so are these, so I should be able to write one set of modes in terms of the others, and vice versa. And this is called a Bogoliubov transformation. Basically, I can always write something like this. Okay? Where you can basically, from the definition of our inner product, and these relations here, which are going to be satisfied also, same relations are going to be satisfied by these guys amongst themselves, you'll find that you can write this guy as, and up to some minus signs. Maybe not all that important exactly, the minus signs and the, but this, when you do this, you can write the annihilation operator in the original basis as a linear combination of the annihilation operators, but not just the annihilation operators, but also the creation operators. You can check that the stars and indices are in the right place, and if they're not, then you fix it, right? But at the end of the day, the important thing is that, first of all, in Minkowski spacetime, you're guaranteed, if these guys are Poincare invariant vacua, you're guaranteed that these guys are going to be zero. Okay? And if they're not, equal to zero in some situation, then as Kyriakos pointed out this morning, then AI acting on the new vacuum is in fact not equal to zero. So there will be, in this new vacuum, there will be particles from the point of view of these guys. All right? And furthermore, we can ask how many they are. Let's call it Ni here. this is simply going to be equal to the sum of J. All right. And now the Hawking effect is going to be precisely due to something like this happening. So let me outline it first, and then I will do a little bit better job of arguing for it. But I'm not going to go into the detail. I would need to really make a convincing case, but you can find that in both. Actually, Hawking's original paper is a very clear description of the calculation. His Communications in Math Phys from 1975 does this rather explicitly and so. Yep.
It's a Bogoliubov transformation. It's already named Bogoliubov before the quantization of the scalar of the field theory. Is this transformation already in place?
Yeah, I think so. I think it's been around for a while. It's.
So before they do quantum field theory in closed space-time, this transformation is already.
I have to admit I'm not too clear on my history here, but I believe was some people were, it dates back to quantum field theory in some condensed matter contexts even. Oh, I'm not sure about it, but.
So for example, if you have a classical field theory and you have a curved space-time, so will the mode of wave function also transformed in this way? I mean, if you don't quantize them, you have a classical field theory with the mode. So
Well, I mean, you are writing actually, these are of course the actual, I mean, if you're not quantizing, then these are just coefficients in some linear combination. And since these guys, so the Bogoliubov coefficients are actually just relating your mode functions. So those are the same, of course. And yeah. Okay. So
excuse me, but after you quantize the field, so then you need to do the transformation for the creation and annihilation operator, right?
right, and this is basically immediately follows from this relation here, and the basically from the expansion here and from these properties that we have here. So it's a few lines calculation to get there. And it's simple here because it's a free field and everything inside is linear. Okay, and so we're going to define our U tilde modes on past null infinity. Okay, so let me draw the diagram that we're referring to here. Remember, this was the black hole formed in collapse. And our U tilde modes are basically providing me, I imagine I have a Cauchy surface at a very early time, sort of in the region at a time when, before the black hole has formed, and I'm by assumption going to claim that this is a Cauchy surface on which there are no strong curvatures or problems like that. And then I will have another set of modes that are describing for me the outgoing waves here at future null infinity. And as Kyriakos pointed out this morning, strictly speaking, I should also be taking into account, and Hawking did this, I should be taking into account the modes that sort of are lying close to the event horizon. I'll have more to say about them when I formulate sort of the information paradox in a few minutes. For the calculation of this thermal spectrum, I'm going to use a very simple model where I don't actually have to worry about the modes. And the point is that these modes that are either ingoing here, well, an outgoing mode at the horizon is of course not going to get out here by definition. And so the way I'm going to do this calculation now, I want to know if there are non-vanishing betas. For that, I have to calculate this overlap integral here. But remember, we established this morning that this inner product here, if you're doing an evolution of the scalar field, it doesn't really matter on which Cauchy slice you do it. And so what I'm going to do, following Hawking, is to actually ask, where did these modes come from under evolution? And what we'll find in a simple model is that we can trace them back. We'll take the mass to be 0 for simplicity, because that allows us to assume that they move along null directions. And we can trace them back here. They will hit, R goes to 0. They will, remember, of course, that's just a point at the center of my sphere. So they will go out here. And you'll notice that the earlier that I'm talking about up here, that's also the earlier down here. Okay? And what you'll find is that these modes can be traced back, but because when my time, retarded time I guess this is called, is going to infinity here, it actually reflects back. There's a maximal advanced time, and we're going to call that, remember this is now Minkowski roughly here, and there's going to be, so basically these modes here, once I've followed them back, see where they came from, they've all come from modes out here that have only a support for v less than this b here. And this is going to be where we get our effect from in this simple model. And then there are many problems with this model. It's oversimplified, but we will. I'll address some of them later on. Okay. So these are the UI modes. These are the U tilde modes, and so our strategy will be to evolve UI modes back from future null infinity to past null infinity. They will pass through the origin and we'll take phi massless for simplicity. Okay. Now, and what I just said is that they will only have support for v less than b. Okay. Now, this is already should be ringing a few warning bells. Because remember, there is a redshift factor that, if we have a mode that's traveling outwards here, they're being redshifted rather sharply, especially if they're coming here from near. There's an exponential redshift with time as you propagate out there. And what that means is that as you evolve them backwards in time, you're going to get a blue shift. And that blue shift is actually going to diverge in the very late time limit. Okay? So you might see that as a problem. Hawking saw it as an opportunity, because what he did there was that he said, well, this means since they're going to have such enormous frequency down here, we can use what's called a geometric optics approximation or Eichel approximation. And in fact, if we're doing this in a geometry where as we should, in a geometry where imagine that we have some collapsing star here, these modes will have such high frequencies that he simply made the approximation that they're oblivious to whatever matter they have to go through. And that, of course, simplifies the computation enormously. So he simply, not only did he turn a blind eye to the fact that he was talking about frequencies much, much higher than Planckian, but he actually used it for good effect in the calculation. But obviously, we need to come back to this a little bit later on, whether this is really, does this invalidate the whole notion of his effect? So you might worry at sort of. Another thing which is going to be, what we're going to find is that when we actually look at this, if you calculate this overlap integral in this model that I'm going to write down in a minute, you will find that the main contribution to this at late times comes from modes that are very, very close to here. So it's coming from modes that are, and it's really coming from the fact that this support is getting cut off here. And as a result, you get rather universal behavior. You get that the characteristic of the outgoing particles that you find at the end of the calculation will have a universal character. And they will, in fact, have the thermal spectrum of certain characteristic temperature, which we call the Hawking temperature today. And that's also basically a feature of, or a consequence of this very simplification that comes from looking at very late times here, so you're basically going extremely close to the horizon. All right. Now, to simplify the story, I'm going to do this in a very simple model. I'm going to look at a model where I just have as I mentioned earlier, I'm going to imagine that I have a hollow shell, spherical, and I'm going to imagine that collapsing, and it's a model that's discussed in detail in the textbook by Birrell and Davis, and I refer you there for details. And it has some sort of, it is probably the shortest way to get to the answer that we're after. So this is okay. And so, rather than draw it all over again, we can use the same picture. Basically, up there, that would be now my shell, the surface of my shell is that curve. On the inside of it, I'm going to have Minkowski. And in fact, because it is a collapsing shell, and I'm patching, presumably for this thing, it actually will have to do something like this. But that's fine. And so I have the shell surface. I'm going to assume that I have, therefore, Schwarzschild outside. I have Minkowski inside. And then I simply have a trajectory for the shell, and I match across it. Okay? And so my waves here, they're propagating backwards in the Schwarzschild background, I patch them across this shell, onto waves that are propagating in a Minkowski background. They get reflected here, and then back again over here. Okay? And I'm going to make some further simplifying assumptions, but an important one is that I'm going to focus only on S waves, so I'll turn this into a 1 plus 1 dimensional problem, and one of the reasons that that's useful is that then I avoid actually having to talk so much about the horizon modes, because this, along with, so I'm going to ignore basically scattering. I'm going to assume that this is a very large shell so that the curvature is very small at the, where the shell is entering its own horizon, and so that everywhere outside the black hole region, curvature is under control, and that I can ignore backscattering from the curvature in the geometry. Okay? And since it's a free field theory, I don't have to worry about the modes interacting so much with each other. And so I'm going to focus on just the S waves. So that's effectively just a 1 plus 1 dimensional model. And this ignoring the scattering from the geometry, that amounts to neglecting so-called gray body factors. Now, obviously, they are significant, and they are part of doing a complete computation. But they sort of come as a correction on top of the thermal result that we're after here. Okay? So we're going to solve the Klein-Gordon equation outside and inside. We're going to match the solutions. And we're going to assume spherical symmetry. And that allows us to do things rather simply. So okay, and we want to solve outside and inside the shell, and that's going to, and then we're going to match solutions. All right. And spherical symmetry is going to simplify the problem considerably. Now, in Minkowski, I can write that as, well, actually in both cases, I can write it in terms of some radial equation. That's radial function, and then I'll have some spherical harmonics. Okay? And so that's a mode function. And if I want to find out what is the equation I have to solve for the outside shell, outside the shell, it's something like this. It's usual centrifugal okay, and so simplifications are going to come from putting L to 0 if I look at the S wave, and the statement that I have a large mass shell, it actually translates into this being very small because I'm looking at R's that are larger than 2m. Okay? And I've put, of course, this, of course, is for the scalar field mass has been put equal to 0. Right? Now, so I'm not really going to work all this stuff out. Point is simply that there's a procedure, it's a fairly simple one. The limits, the assumptions that I'm making will simplify the calculation. And at the end of the day, we're going to have basically be interested mostly in how does this thing depend on advanced and retarded time in the asymptotic regions. So the outgoing mode at squared plus, we'll label it by omega. And this u here is just, as before, it's t minus r star, the torus coordinate. And the ingoing mode is where v is, as before, t plus r star. And of course, both of these modes are in the black hole region, part of the diagram, okay? And now, if you do the matching problem across this shell, and in particular, and this is done by Birrell and Davis, and in particular, you don't think about it in all generality, but you look at it at late retarded times. So basically when little u is going to infinity. Okay? Because that's where the effect is going to come from. So there's some maximal u, which is the location of the horizon in your units. Okay? This is at late times. And this is this exponential redshift that I was talking about. So these are the variables appropriate for the Minkowski part of the geometry. And there's an exponential redshift relating the retarded time down there to the time up there. So it says that as little u goes to infinity, we're getting closer and closer to this basically this thing here is u equals u0 inside the shell. Okay? And and now the reflection condition at r equals to 0, that's in Minkowski space, that's very simple.
Don't you mean the condition on V on the last equation? You want u0 minus u. Shouldn't it be an equation for V?
It's coming. It's coming. Because I'm going to say at r equals to 0, we have u equals v, right? Well, up to a constant. But let's say we have it there. And so we're going to view outgoing mode as having it'll come from an ingoing mode that went through the origin. Okay, so the ingoing mode is going to be a function of v, as you said. And so what we're going to find here an ingoing mode, okay? So now we're almost done, because this tells us that is proportional to, so now I just have to undo these coordinate transformations So I'm going to have some log u0 minus b. Okay? And then, if I assume that, I'm going to assume that, as I said earlier, that the mass of the shell is quite large. And so, there isn't going to be a lot of curvature that I encounter on either side of the shell here. So, I will find that the relation between capital V and lowercase v is going to be just some shift that I can just absorb into my equations. Okay? And so, for large shell mass, space-time curvature is small outside the shell at early times, which is when we're doing this matching. This is the second matching. And we'll write basically V is going to be. And we don't actually need to do a lot of calculation to see this. What we really know is that as we're getting very close to U0, we're going to get a V0. We're going to get a V that is sitting on this curve, and it will simply go to a constant value that we've already declared has this value B here. That's simply by the, you can read this off from the diagram. And since the actual value of B is not going to be important, it's just that it is a sharp. So our mode, and this is almost the last equation I'm going to write here, is going to be e to the minus I omega 1 over our surface gravity from this morning if V is less than B, and it's going to be 0 otherwise. All right. So now I have an explicit function here as a function of omega. I also have an explicit function for the modes. I had it somewhere before. For the in modes, they're going to be just given by simple spherical waves. And so it's now straightforward to calculate the overlap integral. And I'm not going to do it. It is done in Birrell and Davis. But the point is that we can now do this overlap integral on an early Cauchy surface because now we know the functional form of the modes in the variables, of the outgoing modes in the variables that are appropriate on the incoming surface. All right? So, we're going to do this on a Cauchy surface at early times. Okay. So what we're interested in is this guy, beta omega omega prime, which is going to be minus u twiddle omega prime, inner product with u omega star. Okay. And if you do the calculation, you find the following expression for the occupation of mode omega prime coming from a mode omega ingoing is going to go like 1 over omega prime, and then it actually has this characteristic thermal form, minus 1. Okay? With, as we saw this morning, the Hawking temperature is given by, which is, in the units that I've been using, is just 1 over 8 pi m. So that's where units of Planck length. Okay, and so the details on how you do this calculation are in Birrell and Davis, but important thing is that it's an explicit computation you can simply do. All right. Now, there are a few things to note here. First of all, is that this is not a large temperature. You ask what is the Hawking temperature of a solar mass black hole, you find that it's 10 to the minus 8 Kelvin times the 1 over m in solar masses. Okay, that means it's not something, it's hard to get astrophysicists interested in this effect. Second thing is, okay, we're not quite done here. This is just the contribution from a given mode omega. So to get, we should sum over all possible incoming frequencies. And if you do that, you integrate over this expression here, you'll find that it is log divergent. Okay? So let's see, I won't. Well, it's kind of obvious here. Well, so do we have to worry about that? Well, yes, we do, but not too much. This is a feature of the fact that we did this on a static background, and basically it's just telling us that at late times we start seeing this effect, we start seeing an outgoing flux of energy, but that just keeps going on forever. And so at this level of doing the calculation, if we're ignoring the back reaction, we shouldn't be surprised that we get an infinite amount of energy out, because we're allowing for contributions over an infinite period. And so what we'll find is that this will be fixed if we look at back reaction. Then we'll find that the black hole evaporates. And as I mentioned earlier, that can be systematically taken into account in 2D models, and you can get a pretty sort of good intuitive feel for how these things work. But it's not really been done in and as I mentioned earlier, the dominant contribution to overlap integral comes from these late time modes that are very close to the horizon. And that is something we need to worry about, because that's telling us that this calculation features modes that go way beyond Planckian in frequency. Okay. Now there are different ways to address that. I will address it later on today by sort of in a general effective field theory argument. It's not going to be addressed in a quantitative manner there. It's in a very qualitative way. You can also address it in a quantitative manner by, it has been done by a series of papers in the 90s by Ted Jacobson. He calculated sort of the effect of implementing a cutoff or modifying the dispersion relation of this wave operator. in such a way as to suppress the Transplanckian modes. Now the question is, if you do that in the reference frame of these sort of asymptotic coordinates, then of course you're going to you're going to lose everything, because then those modes are not simply there. And the question is whether that's actually appropriate for the physics. And so what Jacobson instead did was that he adapted the problem to a reference frame that would be used by an infalling observer. Basically, at least in one incarnation of this work, there was basically he discretized the radial direction in a frame that's falling into the black hole and asked, do you actually see this Hawking radiation in this case? And the answer was yes, and he could derive the thermal spectrum in a very robust way that seemed to be quite insensitive to exactly how he implemented his cutoff. So that's, you could also do it by modifying putting in some higher derivative terms in the dispersion relation, and that had also the similar effect. Okay. Now I had already mentioned gray body factors. We're ignoring those, so that's something that one would add here. I did mention that if you want to see how to do this, not just in this simple model, but in a more realistic setup in 4 dimensions, then Hawking's original paper is the place to go. And finally, often when people are doing this calculation, they actually do something quite different from this. They don't look at this collapse geometry. They actually make the reasonable assumption, which we're going to make again, certainly more than once in my talk tomorrow, that if you're interested in what's going on over some limited time scale, and we'll see in a moment how limited, so basically on time scales that are short compared to the lifetime of the black hole, once we figure out what that is, it should be a good approximation to actually use the static maximally extended Schwarzschild solution to do this calculation, and one can do that, and it sort of results in a much more elegant mathematical formulation of this computation. And so in that case, you have the two sides of the Penrose diagram, and your scalar field, you define that in a vacuum state on a Cauchy slice that extends through both of those regions. And then you simply implement the fact that observers outside the black hole, they don't have access to the to the other side. And so you trace over those degrees of freedom, and that will in fact give you a density matrix, which is precisely the thermal density matrix at that Hawking temperature. Now there are various subtleties that go into that story as well. The result depends very sensitively on what vacuum state you choose. And again, the appropriate vacuum that you have to insist on using in that case is the one that is basically defined with respect to positive frequency. It's annihilated by positive frequency mode of a time variable, which would be used by somebody falling into the black hole. So basically the Kruskal time variable that we were discussing this morning, and not the Schwarzschild time. If you normal order your fields with respect to, or you use a vacuum that's defined with positive frequency Schwarzschild mode, you get what's called the Bowler vacuum, and that actually has divergences at the horizon. And that may be not surprising, because that is actually the clocks that you're using to define positive frequency are sort of infinitely accelerated when they're very close to the horizon, or that's diverging. And so I may or may not get to that tomorrow if I discuss the Unruh effect. But so there's a variety of ways of doing the computation, I guess was my point here. And at the end of the day, they disagree on many things, but they always end up agreeing on the leading thermal character of the spectrum. So that seems to be a very robust feature of doing quantum field theory in a curved spacetime. You can do it for scalar fields like this. That's the simplest. It has been carried out for spinors and gauge fields. And then you work harder, but you end up with, again, they all have the same temperature here. Okay, so what I now want to do is to ask, so where does this lead us? And in particular, there's this point 2. Where does that lead us? We should include a back reaction now, and so the black hole is going to evaporate. And at least for a while, as Kyriakos mentioned this morning, we expect that since this is a slow evaporation, that the black hole will be, that you can use at any given time during the evaporation. You can calculate this flux that you're getting out. It's going to change gradually with time. The mass of the black hole is getting smaller, so the temperature is getting higher. But for a long period, you should be able to use this. And so I'm going to just sketch rather quickly what sort of the timescales that are involved, and then we will move to worrying about some information issues. Let's see, when did I start? 4:43, okay. Something like that, okay. All right. So we'll take it as established now that a black hole that's formed in gravitational collapse will emit thermal radiation to future null infinity. And now we just want to know how much radiation. Okay? And that's going to be our starting point for considering what you might call black hole evolution. So black hole evolution includes the formation from some diffuse initial matter. If we want to imagine things being in a pure state at the beginning, you'll form the black hole, and then it gradually evaporates. And the question is, how long does it take? Okay, and to do that, we'll use the Stefan Boltzmann law. And that's just to get sort of a rough idea here. If you really want to do this right, you have to include the gray body factors and sort of do a little more work. But at the end of the day, we're just going to use the Stefan Boltzmann law for black body. And that tells us that the energy per unit time that gets emitted, so that's going to be the change in mass, is going to be proportional to, well, it's the area, right, times temperature to the 4th power. We're in 3+1 dimensions. And now we can plug in, and I guess that's a minus sign here. We're losing energy. And so that's roughly minus m squared then is the area in Planck units. This is going to be 1 over m to the 4. Okay? And that tells us that if you start at some time initial with a black hole with an initial mass, its mass at time final is going to be, at least the way it scales parametrically with m, it's going to be given by this integral. M squared dm. And so that's, again, going to be m initial cubed minus m final cubed. And let's assume that this guy is much less than m initial, that we waited a long time so that we're really interested in, let's assume that this guy is just order m Planck cubed. Okay? And this leads us to the notion of a black hole lifetime. Which I'll call tau. That's going to have some prefactors that I'm not going to care about. And it's going to be given by the initial mass over the Planck mass to the power 3 in Planck units. So of course the Planck time is very short, but this is for astronomical black hole is a truly large number. In fact, if you can estimate this, and with the prefactors in place, you get that it's 10 to the 71 seconds if you measure for a solar mass black hole. The age of the universe is 5 times 10 to the 17 seconds, so you see that black holes that LIGO is likely to be detecting are not evaporating anytime soon. Okay. So it's a very long time scale. It goes like m cubed. And it's parametrically long compared to several other time scales in this problem. So this is a long time scale. It's in fact parametrically longer than two other timescales that I want to. And one of them is the so-called light crossing time. That one is of order m. That's really just the time it takes light to travel a distance of order the Schwarzschild radius. That is a characteristic time scale for how, for example, if you form the black hole in a realistic situation, things will settle down rather quickly. So there will be some initial transients, and those transients are dying out on a time scale of order the light crossing time. And after a few light crossing times, you're going to be having, if you have spherical symmetry, you're going to have something which will be just a Schwarzschild black hole with the only feature that characteristic feature is its mass. And there's another time scale which is somewhat longer, but still short compared to and that's the so-called scrambling time, which we will have more to say. But the scrambling time is in these units is of the order of m log m. And that's, of course, in units, in Planck units. So that's a fairly modest extension on the light crossing time, and is still much, much shorter than this m cubed for a large black hole. And so when we are interested in things that should resolve themselves on time scale of order the scrambling time, so things which are going to come up when we're thinking about various Gedanken experiments in black hole backgrounds, that I'll get to either later on now or tomorrow, then it is still a very good approximation to say that the black hole is not really changing very much during that time. The number of photons, if you ask here, each photon here now is going to carry an energy of order 1 over m. Okay? You're going to send off photons for a time of order m cubed. Now the total number of photons that comes out of the black hole is of order its entropy, its initial entropy, if they're carrying off the information. So that's telling us that it's of order m squared photons that are going out, and this matches. If you send off photons, m squared of them, each of them carrying 1 over m, that is going to carry off an energy of order m. And you can see that basically each photon is going out roughly once every light crossing time. So that's telling us that the number of photons that the black hole emits during a scrambling time is quite modest. It's of order log m. But it is bigger than 1, and so we will have to keep that in mind later on. But it's important that we can, this is our justification for working on static backgrounds, is that the timescales we're usually interested in are quite short compared to this lifetime. Okay. So now we've established sort of the characteristic timescales of these problems. Let's ask sort of what happens. Well, so far what we've talked about was a very simple scalar field quantization in a collapsed background. I mentioned this morning that one expects the semi-classical back reaction to lead to an evolution where the black hole loses energy. Eventually there's an endpoint. So let's draw just remind ourselves what this is usually called semi-classical black hole. And so diagram looked something like this, right? Perhaps there was some matter forming this thing. The strong curvature region is around this, and in particular, there is strong curvature close to the endpoint, and there's no avoiding that. The question is, how much do we need to worry about it? And then, as Kyriakos pointed out, the picture here is that you have Hawking radiation going out. Now, almost all of it in this diagram is coming out extremely close to this event horizon. But remember, of course, distances are deceptive. Even though in the diagram it looks like it's all coming very close to the event horizon, it's actually coming out. If you ask over here, this region here where you're getting most of the things out actually is quite a long time. It must be something of order m cubed. That is the time at infinity that it takes to receive all this, all the Hawking radiation. Okay. Now, a new feature now compared to the classical case is precisely this: that if you look at a light ray that is emitted out here, it actually is, there's a final, you might call it an endpoint. So U equals UE is the endpoint. Operation. And this diagram can actually be worked out analytically in this CGHS model or its cousins. And one indeed finds that there is the curvature does blow up around here. There is this last radiation that goes out, is sort of Planck scale in that case. Those black holes are kind of funny because the Hawking temperature is independent of mass. So you don't have this thing that you have in 4 dimensions, that you're going to have an explosion at the end, except the sort of last Planck scale or so is when all these approximations break down, then it's anybody's guess what comes out. But so anyway, if you're going to resolve issues about information, you would better do it in such a way that you avoid having to go through this region very close to the endpoint of the black hole. So now I'm going to talk about how one sort of can do that, or make very general arguments as to how to do that. Okay. And so by the time you're including the back reaction, you're not just looking at the evolution of the matter field here, you're actually looking at an evolution of the geometry as well. Okay? So what we really want to do in this problem, ideally, and what we can do in 1+1 dimensional models, is to actually solve for the dynamical evolution of the combined system of geometry and matter. So even though we can't do it in practice here, we can sort of imagine how we would do it and what the formalism should look like. So we have to have some sort of time evolution, and we have to discuss what we mean by time, of course, in this case, of matter plus geometry. Including this back reaction. To Hawking emission. All right, so that's the goal. And the tool to do that is to use we're going to use effective field theory. And basically, every time that people have been posing the information paradox, they may not tell you, but they are always implicitly at the back of their minds having in mind that there is an effective field theory that describes the process. So let's now try to ask sort of what is that effective field theory going to look like? Well, we've already said a few things about it this morning. So this effective field theory is certainly going to include the leading terms, which are Einstein-Hilbert, matter. It's going to include, presumably, some higher order terms that I'll sort of schematically write here. And these are not all independent. I'm just sort of, okay, and then I can even go further and I can ask for some third order terms, at which point I'll start seeing explicit powers of the cutoff. And as usual in effective field theory, this is going to be a cutoff scale. Okay. And below this scale is an energy scale. This effective field theory should be valid and not otherwise. Now, how do I know what terms to write down? Well, in general, you should write down any terms that are consistent with whatever symmetries that you have in your problem. And for these guys, there aren't very many symmetries to restrict things. So in fact, you can write down quite a few terms. But the assumption that we're making here, and in fact, if you miss them, if you then try to work with this effective field theory, you regulate things, you renormalize, you calculate your one-loop diagrams, then you will find that whatever terms you forgot, they will be generated by renormalization. And so in our discussion, we basically have to assume that this effective field theory contains whatever terms it can. But the basic features that we're assuming is that it is a local theory. The terms are covariant. They involve covariant derivatives of fields. They involve tensor quantities. But beyond that, it can be pretty much general. All right? But the important thing is that for what we're going to use it for, we don't actually need to know the explicit form of it. We just need to know that it is local and that it has sort of not much beyond that. And the reason for that is that we're going to stay at energies and distances such that all these higher order terms that we might have issue with are actually going to be suppressed. So we expect high order terms to be suppressed when, as long as, and now I'm not going to be very precise, but simply some measure of the size of your curvature is small compared to your cutoff scale. Okay? Now, of course, you would need to figure out some invariant measure here, and it can be different things for different geometries, but let's just look at an example. Let's say we find ourselves able to study details of evolution of a one solar mass black hole using sort of current technology in particle physics. And so we'll take a Schwarzschild black hole with, so of mass 1 solar mass and let's take our cutoff scale to be 1 TeV. All right? And now we can ask, how much do I need to worry about, for example, these terms like r squared here? All right? Now remember, we need to calculate something like, what you find is that at the event horizon, let's say we take this Kretschmann scalar, we divide by omega to the fourth, I guess. This turns out, if you put in the numbers, is 10 to the minus 44. So it's going to be pretty small. And in any case, we're going to be making formal arguments. And so we can, in fact, take our mass to be whatever we want. So we can make this actually as small as we like in our formal arguments. And we will. Okay. So now, it's not enough just to avoid regions of strong curvature. The extrinsic curvature of a Cauchy surface must also remain small. So we need to find Cauchy surfaces that are not, that don't have any kinks in them, or this must also remain small. Compared to the cutoff scale. So it's not. So we have to avoid this region here, and we cannot draw arbitrarily silly time slices. They have to be. They have to respect this condition as well. But it turns out that one can still do this, and those are these things that Kyriakos mentioned this morning. These are things called nice slices. Now they're nice in the sense that one expects to be able to reliably apply effective field theory on such slices. So they're very nice if you like effective field theory. As we will see, they're not so nice in the sense that they're precisely on these slices that we're going to run into the problems that Kyriakos mentioned this morning, that is, these inconsistencies between unitarity and the local evolution. So let's see if we can get there before the end of the talk. So, what do these slices look like? Now, I'm not going to, for this time, for once, I'm not going to just ask you to take my word for it. Let's just explicitly construct a set of nice slices for a Schwarzschild black hole. So we'll do it for the eternal Schwarzschild black hole, and then you can sort of think about how you would modify the construction and patch it into a collapse geometry or an evaporating geometry. That's going to be a little bit more tricky. Now these nice slices were, as far as I know, were first sketched by Wald in 93, I think it was. And then we had sort of, based on that, we worked them out in paper with David Lowe and Joe Polchinski and John Uglum and Lenny Susskind. And so we gave that's the construction that I'm going to give you. And then these have been, more sophisticated versions of this have been done by, worked out by Steve Giddings, for sure, and probably some other people as well. So it's sort of a well-established procedure to construct these nice slices. And the way we do that, so there's a simple construction that I'm going to write very quickly here. And it's easiest to do in Kruskal coordinates. And then again, you can refer back. So remember, in Kruskal coordinates, a black hole looks something like this. This is our capital V, this is our capital U. And then we had the singularity sitting here. This was uv equals to 1. Okay. And so our nice slices are going to be, let's first initially just construct one of them, and then I'll give you a prescription for generating the rest of them. So I'm going to consider a hyperbola here inside, and it's an important thing here, and that maybe Kyriakos didn't mention it this morning, but in order to formulate the paradox, the information paradox, we actually need time slices that don't just go close to the black hole, but actually extend into the black hole. So that's what these nice slices will do. So we're going to take a hyperbola in here. So this is uv equals to some constant. We're not going to have it very close to the horizon, but it shouldn't be very close to the singularity either. So this is basically the curve uv equals alpha squared with alpha less than 1. Okay, because it's, and of course greater than 0. Okay, so it's somewhere sitting in here. And then I'm going to take this point here, and I'm going to patch together this segment here, and they even have some colored chalk here. So my nice slice then for t equals to 0 is going to be this. Now remember, I can just label them any way I like, but of course these guys will emerge out into the asymptotic region where I can actually sort of match them. I can identify what is, go somewhere very far away from the black hole and ask what is Schwarzschild time there. And I can use that as a label for this. So I'll call this guy t equal to 0. Now of course t equal to 0, Schwarzschild is strictly speaking here, so it's, you know, I've done maybe some constant shift. So this is my first one there. And mathematically, it's quite simple. It says uv equals alpha squared if v is greater than, is less than u, and then u plus v to alpha if v is greater than u. And of course we'll have to smooth the join here, otherwise we'd get some extrinsic curvature here, but that's easy to do. Now, how about, and then t not equal to 0, it's actually, we use the a feature of the, so again, I'm going to follow that, it's going to be on that hyperbola, if, but now it's if v is not less than u, but u times e to the t over 2m, okay? And then it's going to be e to the t over 4m, u plus e to the minus t over 4m, v equals to alpha on the other side here. So you'll notice that if t is bigger than 0, we're just moving the point at which we do the joining here. And so then I'll continue on some slice like this. And I can continue doing this. Very late slides is going to look more and more. Okay? And I label these with some Schwarzschild time out here. But if you're an infalling observer, it's not hard to show that your, let's say, for example, 3 momentum is going to spatial components of your 4 momentum are going to remain finite as you cross this one here with respect to this time slice. Whereas if you ask the same question in Schwarzschild time here, because of the degeneracy at the horizon, you're going to find that that will diverge. So these are actually good slices for infalling observers. And if you go far away from the black hole, where the Hawking radiation is making its merry way out to infinity, well, these are just pretty much Schwarzschild time slices out there, so they're also going to be good slices there. All right.
What is special with the parameter alpha?
Nothing really. All it needs, you don't want it to be very close to the singularity, because then your nice slice is in a region of strong curvature. And you also don't want it to be 0, because then you're back to Schwarzschild slices.
So we have an infinite family of
Yeah,
slices.
you have freedom to do this. Yes, that's right. Okay. Now, obviously this has some little bit strange features, but the main thing here is to note that with this here, this is a slice, and all of these slices, by construction, they never get closer to the singularity than this hyperbola here. And so if you choose your alpha away from alpha equal to 1, you have satisfied the condition that there is no strong curvature on your slice. If you do your smoothing correctly here, you will find that there's nowhere is there a strong extrinsic curvature either on these slices. So on these slices, you should be able to formulate perfectly nice effective field theory with some Hamiltonian. And now that Hamiltonian is going to generate for you, of course, the evolution from, the Cauchy evolution along these slices. And what you're going to find is that this thing that we will call, it's usually called the nice slice Hamiltonian. So the nice slice Hamiltonian is going to generate some evolution here, but it's not generating a symmetry. It's this nice slice time is not, it is not Schwarzschild time when you're inside the black hole or even near the black hole. So there is going to be some deviations from that. And so it by construction generates time evolution on these slices. Basically, we can write formally it's going to be something like this. And this Hamiltonian, as I just said, it's time dependent. It changes as you move along. But if the black hole has large mass, it's actually weakly time dependent. And that's because we're in, the bigger you make the black hole, the sort of less extreme is the geometry where we're making these, where we're constructing these slices. And as we well know, if you have a time-dependent Hamiltonian, it will produce particles. There will be particle production in the system. And so what you'll find is that this leads to particle production. And if you think about the characteristic scales in this problem, it will actually be at order 1 over m energies. So that's the time scale on which these things are evolving. And that particle production, of course, is in this basically this picture for Hawking. This is how Hawking radiation is generated in this picture. Now, I don't recommend going this route if you want to actually calculate the thermal spectrum. This is not a practical way to calculate Hawking radiation. But it shows us that in principle, there must be a way to calculate it in such a way that you never involve. You see, there's nothing trans-Planckian that happens anywhere on these slices. And so this is a general argument that you should expect to see Hawking radiation. Particle production, which then, if you were to be very strong computationally, figure out what this guy is, work out this evolution, you would no doubt find is going to give you the Hawking thermal spectrum. Now, there are some caveats here, of course. This is a classical construction. It doesn't take the back reaction into account. So basically, these guys, these nice slices, are eternal in the sense that you can just continue doing this forever. Now, we know that's not going to be how it works at the semi-classical level. You will only see nice slices for a finite time there, and you can sort of see it up here, because eventually these nice slices, very far from the black hole, are going to track the asymptotic Schwarzschild time. Well, that Schwarzschild time is going to evolve into this region. And then there is no way to get here on a space-like surface anymore. So there must be a time, there must come a time when your nice slices are going to run into the forbidden region, which is close to the endpoint of the black hole. Now, it's going to take a while to get there. And in fact, you can work out this construction in some toy models, and what you'll find is that from the time that these nice slices in this evolving situation, so early time slices are not going to be inside the black hole. And then there's going to be a period where you're going to have your nice slices that extend inside the black hole, but avoid this region. And the time that you will have from the time that your nice slices enter the black hole region until they run into the endpoint is of course going to be the lifetime of the black hole. It's going to be of that order. And so if you start with a very large, if you're happy with your effective field theory for a black hole of a certain mass, let's call it M0, then you just have to start with a black hole that is much, much bigger than M0 in mass, and then you can evolve for most of its lifetime, and you're still using effective field theory then when there's only M0 left. But M0 was already a very large mass, we said. And so that's usually the game people play when they want to sort of argue that they can avoid, they can make their arguments before they run into this place here, okay? Now, the important thing is that during this time that you have these nice slices operating, they avoid, as I said, strong curvature. The extrinsic curvature remains small, and they have the feature that this can go on long enough that they cover the region out here where the radiation is coming out. So they will actually, these nice slices are engineered in such a way that infalling observers will encounter them at low energy, but the outgoing Hawking radiation will in fact also, most of it, will pass through these slices at low energy. And so this seems like a rather robust way to start addressing questions that, like Kyriakos was beginning to address this morning, that, in fact, what I will start with tomorrow morning then is to establish in a simple way that there will be quantum cloning on these slices if information comes out of the black hole. And that is one way and quite a useful way to formulate the information problem. Now, I've run out of time now, and I'm much further behind than I was this morning. This is a good thing it's only 3 lectures. I would get probably eventually there would be the gap between my ambitions and my achievements in these lectures would diverge at a rate that's faster than the speed of light, and no information would be conveyed anymore. So, but let's hope we manage to convey some information tomorrow.
Thanks a lot.
Which one?
The great body factor. So you said we are capturing and we have an exponential form, then there's some tendency, but we factor that out. So we actually looked at that.
Well, I wrote down, I think maybe it's still there. So the gray body factors come from when you really worry about these terms in your wave equation. Okay, and I arranged conveniently to focus on modes where they're simply not there. So it's just if you solve the problem honestly for all the modes, if you want to get, of course, the total emission spectrum is going to involve not just the S waves, but all the other modes as well. That's where you will start seeing deviations from it. And basically, you know, you see this radial equation. It's written in the form of a Schrödinger equation here. So it's an eigenvalue. It's a zero energy Schrödinger equation. And so they're just coming from basically solving that Schrödinger problem in this potential. So there's a potential barrier actually that separates the outside world from the, you know, from the horizon that you need to take into account.
Okay, then enjoy the evening and see you tomorrow at 9, but let's now think ours again.